Swayam Prabha. Digital India. Educated India.
So then we say that since we have to solve part of speech tag ambiguity, and ambiguity is essentially picking up an option out of many, we are actually solving a machine learning problem, and this disambiguation problem can be solved with data. But before that, let us see what is human beings' attempt at solving the problem using human beings' own brain power, okay, from the understanding of the problem. So we'll come to the data-driven part of speech tagging, which insists that the data is annotated, and since each part of speech has to be found out in the training data, we need part of speech tags -1, these many examples in the training data. So if golf has 2 part of speeches, noun and verb, we need at least 1 instance of golf in the data for annotation. So why 1? Because we can place noun, and whatever is not noun will be automatically placed as verb by the annotator who is creating training data. Okay, so this is a requirement from the machine learning point of view, and we are saying that at least 1 example of golf is needed in the data. Okay, but we need other instances, other examples of part of speech tag, other instances of the class also in the data. So we'll come to this machine learning based discussions little later. But as I said, what is our attempt at creating a rule based part of speech tagger? So I look at the sentence. He gifted me the present, or a present, this present, that present. Here present is noun. They present innovative ideas. Here present is verb. He was present in the class. Here present is adjective. So I've taken 3 major part of speech tags: noun, verb, and adjective. And we have examples of noun, verb, and adjective as data. Okay. Now, by looking at the context, can I come up with a rule that will decide whether the current word is a part of speech, has a particular part of speech or not? So the current word, the word current is important. We bind our part of speech tagging algorithm to positions. Okay, so a sentence is a sequence of positions. The positions are occupied by words. You can take help of this imagery that every sentence is a sequence of cells or rooms where there is an occupant, and the occupant happens to be the word. Now we'll have to place a tag at every position depending on the word at that position and the surrounding words. So I want to disambiguate present for its part of speech. So a common sense rule, a rule that is obvious and suggests itself, is this: if the word present is preceded by a determiner, the, a, this, that, or a demonstrative, which is this, that, then the part of speech tag will be noun. So the question we ask is that this seems like a very, very reasonable rule. If there is a determiner or demonstrative, the, a, this, that, before present, then this present must be a noun. Now the question we ask is, this rule, does it classify correctly? Does it disambiguate or give the correct part of speech tag accurately in all situations, correctly and completely? Okay, correctly and completely, you are, I think, sensing that we are referring to precision and recall. What is the precision of this rule and what is the recall of this rule? Recall is more important. For some applications, precision is important for a different set of applications, but high precision, high recall is always required. So this rule, if present is preceded by a determiner or demonstrative, then the part of speech tag will be noun. Does it have 100% recall? That means it will not miss any instance of present to be a noun. Okay, when it is actually a noun. Okay, it will not miss any such instance. And precision means it will not incorrectly tag a noun, when it is present in the input. Okay, is this a completely 100% accurate rule? Is it a fail-safe rule? Does it have 100% precision recall? Or going back to more philosophical discussions, does this rule have no error of omission and no error of commission? So this is the false positive and false negative situation. It turns out that it is not 100% precision and 100% recall situation. Its precision and recall are not 100%, because you can have false positives in this form. The present case is not convincing. You see, the present here is preceded by a determiner as the rule prescribes, but present is not a noun here. It is an adjective. That is because present is qualifying case, which is coming after present. It also is false negative. Present foretells the future. Here present is not preceded by determiner or demonstrative, and it is missed as a noun if I apply this rule. So it turns out that this rule is not 100% precision, 100% recall rule. Okay, it has false positive and false negative. So this is a very instructive situation and is very characteristic of whole of AI, where we give the description of a conceptual space, and that description does not cover all instances, which means its recall is less than 100%, and it accepts things which are outside that conceptual space as a correct one, which is a case of false positive. And false positive lowers the precision. So I suppose you are convinced that this rule is not 100% precision, 100% recall rule. So then we see if we can repair the rule. Okay, you can increase the boundary to embrace more instances, to capture more instances, and at the same time not admitting wrong instances. So you know also from machine learning that both precision and recall cannot be guaranteed. You sacrifice one for the other. The precision versus recall curve is a falling curve. Okay, recall on x-axis, precision on y-axis. It is a falling curve. You gain in one, lose in the other. So if present is preceded by determiner or demonstrative or followed by a verb, then part of speech tag will be noun. So we are trying to increase the scope of the rule. So present will foretell the future. This case will go through. Will is a verb. Okay, so this or clause will apply and present will be tagged as noun correctly. Present foretells the future. Foretell is a verb. So this rule will be fine. Again, we ask, is this rule covering the whole conceptual space? Does this guarantee 100% precision, 100% recall? So you can think about this and also notice that this or is important here. Or cannot be substituted by and, because then it will be over restricting the rule and it will miss many legitimate noun instances. Its recall will fall. So now just take it as an exercise to see if this particular rule is also completely fail-safe. Will it have exceptions in terms of positivity and negativity? If present is preceded by determiner and demonstrative, or is followed by a verb, then the part of speech tag will be noun. Is this absolutely correct and complete? So think about this. Okay. The first question was to find an example of verbal, a word which is functioning as verb, though inherently not a verb. That was the first exercise question, thinking question. The next question is, this rule is given. Does it have 100% precision and recall? Okay, come up with an exception to show that it doesn't have 100% precision and recall. So rules are always challenged by new data. Therefore, we need a robust system. And there were many attempts at creating part of speech tagger by this kind of rules. A linguist would sit down and give this kind of rules for solving the part of speech tag problem. But always new instances would come and challenge that rule, and the rule will be found to have holes in it, okay, shortcomings in it. So then a community, which is the community of data-driven approaches to an AI problem, came up with a brilliant idea about how to do machine learning based part of speech tagging. And the technique they found useful from their repository of tools is hidden Markov model. So this was very ingenious. It was a very effective move to marry the hidden Markov model technique with the problem of part of speech tagging. So that's why I chose part of speech tagging to show the marriage of machine learning and NLP benefiting both. So the part of speech tagging is an umbrella of very rich problems for machine learning techniques, to test machine learning techniques. And NLP is getting benefited by the very important problem of part of speech tagging being solved by an established machine learning technique called hidden Markov model. Now, hidden Markov model proposed based on Markov assumption about limited window, found usage in automatic speech recognition very heavily. So machine learning is applied to speech recognition quite extensively, even including deep learning today. And some of those examples we'll see. And you have another course on automatic speech recognition. So Jelinek, who used to work in AT&T Bell Labs, he gave this technique for part of speech tagging using hidden Markov model, inspired by automatic speech recognition. The basic idea was what is called the noisy channel metaphor, noisy channel model. So here W comes in, which is a sequence of entities W1 to Wn, and we get levels T1 to Tm on the output side. Here we choose W and T because this is the notation we'll use going forward. W is a sequence of words, T is a sequence of tags, the problem that we are trying to solve. But in speech recognition situation, this W was a sequence of segments of speech signal. So I utter, this is a red tomato. This is a red tomato. Then the first task that happens in automatic speech recognition is word boundary detection. Okay, so from the speech signal, you identify the region corresponding to the word the. This is a red tomato. So this is called segmentation and alignment. We take the speech signal, we cut it into segments and map the segments to the corresponding words. You can go still finer because the words again can be broken into syllables. So this is a red tomato. Tomato has 3 syllables in it. Tomato. So you can go up to the syllable level. Red has only 1 syllable, and you can cut the speech signal, which is a waveform. Okay, we will again find some time to discuss this point. The waveform is cut into segments, and these segments are mapped to corresponding syllables, characters, or words depending on the granularity of the output you want. So in comes a speech signal, out goes a sequence of words. There is a very important problem called single word recognition. Okay, single word recognition, where a word is uttered and the corresponding word is output. This is speech to text conversion, single word recognition. And there the technique that was used was hidden Markov model. Now here we are depicting the problem formulation using hidden Markov model. So this is through what is called argmax computation. We are interested in the best possible tag sequence given the word sequence. The term best possible is made crystal clear by this notation here. We take that particular T as my option, which has the highest probability. Now you see how we are solving the classification problem. We are converting it into a ranking problem, a probabilistic scoring problem. So given the sequence of word, find the probability of all possible tags and take that tag sequence, okay, which has the highest probability. Okay. Similarly, the opposite problem will be given the tag sequence, get the best possible word sequence. So this is W star. So it will be useful for you to remember this notation, the star notation and the argmax notation. Argmax is a function which first of all maximizes its argument, okay, its argument, and gives that argument as the answer. So it is maximizing probability of T given W. As a side effect, it is picking T as the value of T, which maximizes P. So notice the difference between max function and the argmax function. Max function maximizes a function. Argmax function maximizes the function but returns the tag, returns the argument. Okay, returns the argument. So max of fx will be fmax. Argmax of fx will be xmax. Okay, fmax versus xmax. So here T is being returned as the highest probability tag sequence. So now we go into the mathematics of part of speech tagging. I'll give you a top level view of this. We'll do the details in the next class, that is tomorrow. What happens is that probability of T given W is converted into probability of T into probability of W given T, the prior into likelihood. And you are supposed to divide it by the denominator PW, but PW is not affected by argmax because argmax is on T. So PW is not affecting, so it can be dropped. Now PT, which is a tag sequence, is broken up by joint probability and conditional probability into a sequence of conditional probabilities. Then you apply Markov assumption. You ignore all the tags which are one window before. Okay, and then you get what is called the bigrams. You have probability of T0, then probability of T1 given T0, T2 given T1. This was actually T2 given T1 and T0. This is by the law of probability, the chain rule. But I'm ignoring T0 because T2 is affected only by T1. That is my Markov assumption. So you have a product of probabilities in the form of bigrams. Probability of Ti given Ti minus 1. That was the prior probability part. The likelihood probability part is also similarly treated. First apply joint probability, apply chain rule, apply Markov assumption. The word depends only on the tag, and then you have another set of probabilities, probability of Wi given Ti. So you have this set of parameters, probability of Ti given Ti minus 1 and probability of Wi given Ti. These parameters are your building blocks for creating the part of speech tagger, which is done by converting these parameters, but not by converting, placing these parameters in a hidden Markov model. This is a hidden Markov model which is a probabilistic finite state automaton. Okay, so these mathematical details and the algorithmic details we will do as we go ahead during the discussions tomorrow and on Thursday in this week. So right now, I think I will look at the questions that you might have. I see some questions here. Rishi Agarwal, isn't rule-based part-of-speech tagging a cyclic problem? Rule-based part-of-speech tagging is a cyclic problem. Why do you say that? Why is it cyclic?
So because for knowing the tag for the current word, we need to know the tag for the following word or the previous word.
Yes. So following word is a problem, but we'll see an algorithm which is called conditional random field, or by LSTM for that matter, for which it is not a problem, but we build the tag sequence incrementally. That means we get the part-of-speech tag at current position based on the previous positions. So that is okay. I mean, the rule application will not halt because of this problem. But rule-based systems, yes, they have to do left to right processing.
Okay, sir. Thank you.
Yeah. Then audit requirement. Audit requirement we would think is doing assignments. Okay, you don't have to write the end sem examination or the mid sem examination. It will be mainly assignments. And as you know, in this course there will be heavy weightage on assignments. Then Mahesh says, what is the noisy channel here? Does it represent problem of word boundary detection? Yes, it is noisy channel because it introduces its own imperfection into the input. So the output that comes out is not a fully correct output that we desired. It gets corrupted by the insufficiencies or deficiencies in the channel. Nikhil asks, is the argmax equation the subscript should be reversed, right? In the argmax equation, the subscript should be reversed. Which argmax equation, Nikhil?
So the first noisy channel slide.
First noisy channel slide. T star equal to argmax PT given W. Oh, I'm sorry, yes. Yeah, this W and T should be reversed. Yes, that's true. T star depends on only T, W star depends on W. True. I'll get this corrected. Then why is the difference in Pranav is asking, why is the difference in tag sequence length and word sequence length? No, there is no difference. Okay, so TM, T1 to TM and W1 to WN are only for illustration. For tag sequence, the length will be exactly same as the length of the word sequence. No, but caveat for English, okay. For Marathi, not so. We'll see that. In case of noisy channel model, won't every word be given an output tag? This is from Nunna Apurva. In case of noisy channel model, won't every word be given an output tag? Every word will be given an output tag. Yes, that is true. That is true. So noisy or non-noisy doesn't matter. Every word will have to be given an output tag, if possible. Okay. Then Ashish Agrawal, do we have project in this course? Yes, there will be project in this course. We'll come up with a project list little later after we have built up some background. But assignments will happen. There will be the first assignment on part-of-speech tagging soon. This is from Ashish Agrawal. Then Kaveri says, for rule-based pause tagging, can we say we will not require manually annotated data? Yes, that's true. Rule-based systems actually try to get rid of data. Any rule-based system tries to do that. In fact, the problem of deep learning is the scarcity of data. So people are going back to and seriously combining rule-based systems with part-of-speech tag-based system. Okay, this will be an important topic in the course. Drumil says, following the UL system, the grammatical tag is lost, right? As we simply show the functional tag. Yes, the grammatical tag is. Let me answer this question in the next class, okay? Because you need both grammatical and functional tags. Then Fazlili Bora, could you please make the slides available in advance? Yes, from next time. Yes, note taking would be easier then. We are trying to see if the lecture video as well as slides are available right in the beginning, well in advance. Yeah, we'll do that surely. So I think I have taken all the questions. Okay. If there is any other question from anybody.
So my question is like you said for different languages we need different PO taggers, right? But in real world, like there are multilingual languages.
Yes.
So how do we handle that?
Yeah, you are referring to code mixing.
Yeah.
So code mixing. So you remember the first example in the we remember the example in the first class. इस हर्ष स्थिति में भी हर्ष का हिम्मत. So pause tagging for code mixing is a very important challenge in the current world today, and you can read papers by Noah Smith, okay, who has created a part-speech tagger for noisy text, and there are papers on code mixed pause tagging, and I'll refer to some of them. Can you explain the assumption a word is tag? Yes, this is the independence assumption. So the chain rule had many conditioning random variables, but we say that the word depends only on the current tag. Word at a position depends only on the tag on that position. So you are, I think, finding it a bit strange because the tag is determined by the word, not the other way. Okay, but this is a statistical technique, algorithmic technique that Jelinek employed very brilliantly. Okay, so now the class timing is also over, so we will sign off and meet tomorrow. Thank you.